Okay. But we haven't talked about concavity. So let's talk about that a little bit. So I guess we need to talk a little bit about what is concavity. So we can talk about a function being either concave up, or we can talk about a function being concave down. And an easy way to remember that is concave up holds water. So if you have a curve like this is concave up, right? You can imagine that being a cup and it's holding water. Concave down is a shape like that. Right? So it doesn't have to make a complete cup, but if you only have a little portion of it like this, right? That's concave down. Okay. So the second derivative tells us a little bit about concavity. So the function says let f be twice differentiable on an open interval. In other words, you can find the derivative, the second derivative. If f double prime of x is greater than 0, right? So if your second derivative is greater than 0 for every value of x in the open interval, then f is concave up on that interval, right? So the second derivative being positive means that it's concave up. If the second derivative is negative, right, if f double prime of x is less than 0 for every value of x in the open interval, then f is concave down on that interval. It's concave down. All right, so let's see if we can sort of wrap our heads around this intuitively, what's happening here for this, right? So our first derivative is the rate of change. Right, it's the slope of the tangent line, but it's the instantaneous rate of change. So if you take the second derivative, it's the rate of change of the rate of change. You know, when we're talking about rectilinear motion, where the first derivative of the position function was velocity, the second derivative was the rate of change of velocity, which turns out to be acceleration. Right. So if you look at let's look at the concave up for a second. Right. So we start here. At our function at this point has we'll give it a slightly positive thing. So there's our tangent line. Right. It's got a slightly positive slope. So our rate of change is positive here for this. Well, as you move along to the right, I've drawn in a couple tangent lines. As you move along to the right, the slope of those tangent lines gets steeper and steeper. It means the first derivative is increasing, right? That's what the second derivative is measuring. It's measuring the rate of change of the first derivative, and the first derivative tells us what the slope of the tangent line is. So it means the slope is getting bigger, it's getting steeper if it's positive, right? So that's why it's concave up. If it starts going, if it gets less and less steep, if it's decreasing, right, then you're going to get a concave down slope. So in that rectilinear motion, if it's decreasing, it means your rate of change, it's slowing down, right? Till eventually you might get going in reverse. Okay, so that's our theorem. So we're going to do the same sort of thing for this to figure out what where a function is concave up or concave down. We're going to do the same thing we did with the first derivative, except we're going to do it with the second derivative. So we know that the first derivative is 3x squared minus 3x, 3x squared minus 3. Oops, just a pen. But the second derivative is just 6x. Okay. So we're going to use a sine chart to determine concavity, where it's concave up and where it's concave down. Okay, so we're going to set that equal to 0. So you set the second derivative equal to 0, and you get x equals 0. At 0, the second derivative is equal to 0. So we're going to test the sine of the second derivative. And from that, we're going to draw a conclusion about the original function, f of x. Okay, so I'll try to use the same color code we used last time. So here we go. We've got two intervals. We've got from negative infinity to 0. We're always using open intervals for concavity. And then we get from 0 to infinity is the other interval. So we need a test point in each one. Let's pick a nice easy point. How about -1 and +1? So let's check the sign of the second derivative. So the sign of the second derivative, if we evaluate -1 in the second derivative, we're going to get -6, right? That's less than 0, right? It's negative. So it means our function must be concave down on that interval. So that's our conclusion, right? Therefore, f of x is concave down on this interval from negative infinity to 0. So do the same thing for this other interval from 0 to infinity. So for that, we're using a test point in the second derivative, right? We're plugging in 1. So we get 6 times 1, which is just 6. That's positive, right? And so from this, we can conclude, right? Therefore, the original function f of x is concave up on 0 to positive infinity. I should close that. Okay, so we're using the derivative now to tell us things about what's happening in your function, right? The first derivative is telling us how quickly it's the rate of change, how quickly it's increasing or decreasing, right? It's the instantaneous rate of change. The second derivative is telling you how, in what direction it's bending. You can think it's how fast that rate of change is changing, right? Whether it's slowing down, right, which means it's concave down, right, where it's getting less and less steep, or whether it's sort of speeding up, and if that case it's getting more and more steep, it's concave up. Okay, so I wish I'd thought of taking a screen capture of my calculator beforehand, but maybe I'll pause this and pull up the screen capture for that. But you should do that on your calculator. Look at the graph and see, look what's happening at x equals 0. On the left side of the graph, it's concave down, and on the right side of the graph, it's concave up. These cubic functions, I think it's pretty clear that you can see where it's concave up and concave down, which is one of the reasons why it's a good first example for this, because you can see so clearly where it's concave up or concave down.